This week we looked at springs, and everyone found the key characteristic about springs, which is that they bounce back. Um, so on page 46 in your notes, I'd like you to take these notes. So all springs bounce back to a rest kind of position or an equilibrium position when they are either stretched or compressed. So you looked at springs like this, which stretch when weight's applied. You looked at some springs kind of like this one in the jumping bug, which compress when weight's applied and then they bounce back to their original position. And I actually just found this one in my kitchen. So you squeeze it and it kind of springs back. So everything that kind of acts like this, we can think of as a spring. So another thing like that might be an elastic band, like a hair tie or a rubber band. It stretches and then it bounces back to its original shape. And the thing about all of these, that bouncing back, that motion, that acceleration, it all has to do with forces. So this is still kind of in our forces unit, and we're exploring forces on a spring or forces having to do with a spring. So springs exert what's called a restoring force. Restoring meaning that it will return to its original position. So if it was stretched, it will pop back. If it was compressed, it will become longer. A lot of the problems that we think about or focus on in this class, though, are about the extension springs, not the compression springs. So if we're interested in exploring this force that springs actually exert, we are going to look at a free body diagram, as always. So if I have the same spring kind of at different time slots where I've hung one mass from it, we know that the force of gravity acts downwards, and we can calculate that by the mass times 9.81, the acceleration due to gravity. And if it's hanging here in equilibrium, it's not bouncing. And actually, springs sometimes will really bounce, and that's a conversation for another day. But if it's in equilibrium, then the spring, then we know there must be a force that's kind of balancing it out, and we're going to call that the spring force. So because it's in equilibrium, that spring force is equal to the force of gravity in this case. So what is interesting to explore and what scientists have explored in the past is if I hang, a 50-gram mass, and actually many of you did this, if I hang a 50-gram mass from my spring, how far does it stretch? And then if I double that, does it double the stretch? So is it a linear function or is it a quadratic function or some other function? And if we took a bunch of data and actually looked at all of our springs in this way, which I left it kind of open-ended for you guys, so you didn't have to do it this way, and I didn't even expect you to do it this way, we will find that it is indeed linear. So the more force you apply to a spring, the more it will stretch. And so we'll characterize this stretch as x, the change in length of the spring from equilibrium or rest. So if I have a spring with no mass, and this is its position, if I hang a mass m, it will stretch some amount x. If I hang a mass 2m, it will actually stretch 2x. My picture maybe is not to scale. So if we were to graph this, we would get a linear relationship. And like all graphs this year, we're going to look at the slope. Well, the slope is going to be basically the change in the spring force over the change in length, or in newtons per meter. And this is going to have a special value. This is constant for all springs, or for each individual spring, and it is called the spring constant. So K is the spring constant. It's a lowercase k, if you're interested. It's measured in newtons per meter, and it tells you how hard it is to stretch. So more newtons to stretch 1 meter means it's really a stiff spring. It takes a lot to stretch it. So from this graph and this recognition of the spring constant slope, we can derive the spring force equation. That the spring force, so that's the y, we're thinking about y equals mx. So y, the spring force, equals m, our slope, the spring constant k, times x, which actually our x-axis is x. X meaning the change in length from equilibrium. Sometimes you'll also see this with a negative sign thrown in here. I'm not going to throw it in there. All that negative means is it's a restoring force. So it's going to take the change and like undo it. But we don't need to worry about that. This is in our reference tables. So you might have questions that say like, find the spring force or the force from a spring. You would need to know the spring constant if that's what they're asking for, and the stretch of the spring. We'll do more problems like that in class. Have a great break. Happy solstice. Enjoy the longer days.